Okay, so let's go over the activity that we did on standing waves. The specific activity that I'm going to be talking about is doing a simulation, and so it may be that in a future version of this class we'll do it with actual oscillators. Nonetheless, this link here will take you to a simulation, and it's a good thing to do even if you have done the physical demonstration, so that you can really get a grip on systematically seeing what changes cause which effect. So in my simulation here, see, I'm going to go ahead and open that. In my simulation, I'm going to change the parameters as is suggested in here. The tension is going to be set to 20 newtons. The mass per unit length will be set to 1 gram per meter. And just as a way of kind of reviewing ourselves, what's going on here, the different wavelengths here are given by this formula. Well, we can actually figure out what this formula is here if we say, okay, there's a length of a string, and it's going to, for example, oscillate up like this in one moment, and it'll go down like this in the other moment. So it'll go up, down, up, down. In that case, we can actually see that this is 1/2 of a wavelength. So here's one full wavelength actually takes up 2L. So if a wavelength is equal to 2L, this is our first mode. And so you can see when n equals to 1, we have 2L as our wavelength. If we have the same length, but we actually have 2 half wavelengths that fit into here. So in one moment, this part's going up, this part's going down. In the next moment, this part's going down, and this part's going up. We can see that we have one wavelength is actually fitting in the same length as the string itself. So in this case, the length of the string is equal to lambda. This is the n equals to 2 case. 2L over 2 is just lambda equals to L. And then finally I'll do one more case here, which is if we have 3 half wavelengths that fit in between, then one moment will actually look like this, the next moment will actually look like this, and we can see that 3/2 of a wavelength is now equal to L, where again L is the distance across here. So I want you to be able to derive those kinds of things and to be able to think about, well, how many half wavelengths are there? For the n equals to 3 mode, there's actually 3 wavelengths that are actually fitting into this. Also, I just realized I should probably get out the worksheet that's associated with this here. And we can fill it out together as we go. Okay, very good. So in this case here, you can see that 3/2 of a wavelength equals to L, or in other words, wavelength is equal to 2L over 3. So notice that this is like wavelength is equal to 2L over 2, and this is like wavelength is equal to 2L over 1. So again, here we have like a 1, 2, and then a 3, right? It's just like this formula over here. So if you have a mode number 5, you just do 2L over 5. If you have a mode number 17, it'll be 2L over 17, etc. Now, wavelength and frequency are related to the speed of a wave. And if you remember, we're not talking about the speed of sound wave. We're talking about the speed of the transverse wave on the string, or on a rope or a string. Sometimes I use those words interchangeably, but here we're talking about a string. And so you can see that just by solving this equation, V is equal to lambda F, that's one of our key equations in the course of musical acoustics. By rearranging that here to solve for F, I see that F is V over lambda. And lambda is just this lambda that we solved for over here, which is 2L over N. When we plug that in, we see that that N actually pops up to the top. And so that subsequent harmonics, or later frequencies, are just multiples of the fundamental. This can be seen in chapter 8 of your textbook here. You can see that the fundamental frequency here has 1/2 of a wavelength going across. The second harmonic has 2 half wavelengths. The third harmonic has 3 half wavelengths, and so on. 4 half wavelengths, or in other words, 2 full waves, and then 5 half wavelengths, etc. And so that's how you can sort of think about that. And the arrows drawn up and down are reminding you that these parts here are moving up and down, whereas the nodes, the parts in the center here, or the parts over here, are not actually moving at all. In fact, you could put your finger right next to that string and you wouldn't feel it vibrating up and down at all. So, and lastly, I'll just mention that remember that the speed of a transverse wave on a string or a rope is only determined by the tension and the mass per unit length, nothing else. So that's our setup, and that's what we're working with today. The first three harmonics are shown here, so I could even write n equals to 1, n equals to 2, n equals to 3, and so on. That helps us kind of get oriented here. And we can see that this is one wavelength, so it's 3.5 wavelengths, for example, for this wave here. And we did solve the pre-lab questions in class, but let's go ahead and just also do these here. So the speed of the wave on the string is faster. Will the natural frequency increase or decrease? Well, going back to equation number 2 here, I can see that the frequency is proportional to the speed. And I'm going to rewrite that here. So for this one here, F1, the fundamental frequency, is equal to 1, that's n equals to 1, times V over 2L. So in other words, if that's true, if the speed gets faster and the length stays the same, if this guy goes up, this guy will also go up. So I will say that the natural frequency will increase. Furthermore, if the speed goes up by a factor of 2, I can also see that the frequency will also go up by a factor of 2. That'd be like multiplying this side by 2, and then this side would have to be multiplied by 2 as well in order for the equation to still be true. If the third harmonic, question number 2 now, if the third harmonic has a frequency of 600 hertz, the fundamental frequency is what? So to answer this question, we might go back to looking at what these different harmonics mean. So here's our first mode, second mode, third mode. These correspond to the first harmonic or fundamental, second harmonic, third harmonic, fourth harmonic. That's what that means in that language. And we can see that the third harmonic, or the n equals to 3 here, is exactly 3 times the frequency of the fundamental. So, oopsies, I'm not sure what happened there. If we have the third harmonic, so I'll work that one right down here. If the third harmonic, that's F3, is equal to 600 hertz, I know that that's 3 times the fundamental, according to my equation number 2. And so therefore, I created a relationship now between the fundamental and the third harmonic. So that means that F1 must be equal to 200 hertz. Finally, the third question says, a musician playing a string instrument uses a finger to push the string tightly against the fingerboard of the instrument, shortening the length of the string. This causes the fundamental frequency to increase, decrease, or not change. So here we again look to the formula. So the fundamental frequency formula that we use here is F is equal to V over 2L, where L is the length of the string, and V is the speed of the transverse wave on the string. And so I can notice here that if the length of this string changes, for example, if it becomes smaller, then the fundamental frequency must get larger. So I would say that it would increase. And actually, interestingly here, if the length becomes shorter by a factor of 2, the frequency will become higher by a factor of 2. And this can be seen if you compare, for example, a violin, which has usually a higher pitch register, to a large instrument such as a bass, which can be even a stand-up bass, which can be more than 1 meter long strings. You can definitely notice intuitively that the longer the string, given the same other parameters such as the mass per unit length and the tension, will lead to some similar result. Will lead to a result such that the length of the string will mean a much longer length of the string will lead to having a lower frequency, or in other words, lower pitch. Okay, so now let's get to our actual part of our inquiry here. So if we're doing this experiment using this mechanical vibrator, it's basically shaking this thing up and down, and we see that the string is oscillating. In other words, that there's waves being sent that are reflecting back and forth, and this creates something that's called as a standing wave. And that means that it looks like the wave's not going anywhere, that there's just places that are moving up and down, but actually what's really happening is that there's waves that are traveling to the left, traveling to the right, and back and forth, and those are interfering with each other. In other words, waves just add. That's another fundamental principle that we have, is waves are just adding with each other. And we're exploring the different frequencies that create these different modes. So let's go ahead and perform our experiment here using the simulation. So here, if I have, I'm just going to turn the sound on for a moment. And as I increase the frequency here, well, it seems that I don't have sound. Oh no, we have sound. It just wasn't very loud. So there's my n equals to 2. There's my n equals to 1. We can use the fine-tune controls to get this to be as big as possible. Oh, let's look at us a little smaller, a little bigger. Looks like that might be about the right amount. So I'm going to write my n equals to 1 mode has a frequency equals to 70.6 hertz. For this activity, it's probably not necessary to go out to the last digit of precision. We're just trying to get a general idea of what's going on. And if we continue up, it looks like at n equals to 2 is f2 equals to 141.1 hertz. And it looks like we have 2 half wavelengths that appear. So I'm going to say the number of half wavelengths that actually appear. And I'll start drawing these pictures here. Number of half wavelengths that appear. I would say that this one looks something like this and like this. The second one looks like something like this. The third one looks something like this. I'm already sort of drawing what these are going to look like here. Going back. Now let's continue up to higher frequencies. So this one seems to be n equals to 3 at f3 is equal to 211.4. N equals to 3 has f4 has f4 equals to 283.5. And finally, there it was. Finally, n equals to 5 has f5 equals to 353.8. Okay, so I'll turn off the annoying sound, go back to the sheet here. So our n equals to 4 mode had 4 half wavelengths that fit into our diagram there. This one's going to be a little trickier to draw. So 1, 2, 3, I think I got it right. 1, 2, 3, 4, 5. Bingo. So I had 5 half wavelengths that fit into that. So notice that this one here is approximately 2 times f1. This one here is approximately 3 times f1, because 3 times 7 is 21. So this is approximately 3 times f1. This is approximately 4 times f1. And this one is approximately 5 times f1. I'm just going to write approximate, because it's, of course, not exactly equal. But it's pretty close, right? So anyway, so those are the mode number that we would say means n equals to 1. We don't write f1 because this would be the frequency associated with mode number 1. The driving frequency here is shown, and the number of half wavelengths that we see here is, we see 1, 2, 3, 4, 5 half wavelengths. So it's actually, the mode number is the same as the number of half wavelengths. Good. All right, so now we'll move on to the next questions here. Find the wavelength of the measured standing wave using a tape measure when the wave is in the n equals to 2 mode. So fortunately, we wrote down the different modes that are associated here. So I can just go right on back to 141. Actually, I can just even, well, it's close enough here. 141.1. And I can say that let's see, this frequency here is equal to, this is f2, is equal to 141.1, and that is the n equals to 2 mode. And that's actually a place where lambda is equal to the length. And if you notice that the length is from 0 to 100, so that is actually 100 centimeters is my lambda, that's equal to 1 meter. And so interestingly here, if I have a frequency and I have a wavelength, I can figure out the speed of the wave. So v is equal to lambda times f, and that's equal to 1 meter times 141 hertz, and that will be 141 meters per second. So that's the speed of the wave. If we wanted it at a higher frequency, we should increase the tension, as we discussed earlier in the prelim. And we're going to use the equations in the intro to calculate the speed of the wave based on the tension and the mass per unit length. So that's the tension here and the mass per unit length. Now the important part is to make sure that you write mass per unit length in grams per and kilograms per meter, which is SI units. So using our equation here, so our equation is V is equal to the square root of tension over mass per length. We're going to write our 20 newtons, and then our mass per unit length is actually 0.001 kilograms per meter. So these are our correct units here. And when I plug all those in together, I'm going to take out my calculator. When I use my calculator here, I say that it's the square root of 20 divided by 0.001, and I get 141.4. So I have 141.4, and that's meters per second. And this number here is connecting to the number that we figured out in the activity. So if you're understanding this, how to calculate the speed of a wave and how to use wavelength and frequency in order to estimate the speed of your wave, then you're on the right track.